Welcome back to the deep dive. It's really great to have you with us today. I actually want to start by asking you a question.
Okay, go for it.
Have you ever looked at a robot, maybe a Roomba or, one of those Boston Dynamics dogs you see online, and thought to yourself, why is this so hard?
Why is what so hard exactly?
Just existing, moving around, doing completely basic things because, we look at computers and they can calculate pi to a billion digits in a fraction of a second.
Right.
They can beat grandmasters at chess. But if you ask a robot to just fold a pile of laundry on the couch, it looks like it's having an absolute existential crisis.
It really does.
It's slow, it's clumsy, it completely short circuits because it found a sock it didn't expect.
Yeah, that is the classic paradox of AI. The things that are incredibly hard for human beings, like calculus or navigating huge databases, are just trivial for computers.
Right.
But the things that are easy for humans, like walking across a messy living room or folding a towel, are staggeringly difficult for computers.
And that paradox is exactly where we are going today. If you've been listening to our previous deep dives, you know we've spent a lot of time in what we've been calling textbook land.
Textbook land. It's a very safe, lovely place to be.
It really is. Because in textbook land, the world is just a grid. You know exactly where everything is.
Nothing moves unless you move it.
Exactly. If you want to solve a problem, you just line up the logical steps, you press enter, and the computer spits out the perfect answer. It's abstract.
But it is definitely not real.
Not at all. So today, we are dragging the AI out of that pristine ivory tower and dropping it straight into the mud.
We are entering the real world.
The real world. And based on the source material we're looking at today, the real world is an absolute nightmare for a logician.
It is a nightmare because in the real world, you don't just have pure logic. You have ticking clocks. You have bank accounts that actually run dry.
Right, real limitations.
You have batteries that die. You have sensors that give you bad data because the sun is in your eyes. And perhaps the most terrifying variable of all, you have other people.
Other people are undeniably the worst variable in any plan.
They are complete agents of chaos. So the source material we are covering today, it's Chapter 11, Planning and Acting in the Real World. It's entirely about bridging that gap.
Right.
How do we take a system that is, at its core, a glorified calculator and turn it into something that can manage a spacecraft or run a massive factory floor or coordinate a military campaign?
Basically, we are talking about the computational difference between a machine that plays a board game and a machine that can bake a cake in a kitchen that is currently full of toddlers.
That is a terrifyingly accurate analogy.
Oh, yeah.
But yes, that's exactly it. And to do that, we have to rebuild our entire understanding of how AI plans from the ground up.
So what's the roadmap? We've got a lot to cover.
We're going to hit 4 massive pillars today based on the text.
Yeah.
First, we have to talk about time and resources. This brings us into the discipline of scheduling. It's not just about what to do, but when to do it, and with what tool.
Right, because things take time.
Exactly. Second, we have to talk about hierarchy. How do you plan a massive multi-year project without getting totally bogged down in microscopic details right from day one?
Makes sense. And the third?
Third is uncertainty. What do you do when the lights literally go out or when the map you were given is just plain wrong?
And the fourth pillar?
Multi-agent systems. How do you behave when you aren't the only one trying to change the environment? Basically, how do you play a game of tennis without crashing into your doubles partner?
It really feels like we are basically building a brain today. We're taking that cold, isolated logic engine and giving it an internal clock, a sense of scope, eyes to see in the dark, and finally, some social skills.
We are certainly attempting to. And for you listening, the real value here is grasping the sheer scale of that computational gap.
Yeah.
I promise you'll never look at a robotic vacuum the same way again once you understand why just opening a door is a mathematical minefield.
All right, let's unpack this. Let's start with that first big hurdle, the ticking clock.
Okay.
Segment 1, time, schedules, and resources.
Right. To really appreciate this, we have to quickly look back at classical planning, which we've discussed in earlier deep dives.
Right, the textbook land version.
Exactly. In that world, an AI really only asks 2 questions. What action do I take, and in what order do I take them?
Just a sequence. Step A, then step B, then step C.
Right. But notice what is glaringly missing from that entire sequence.
Time. The duration of anything.
Exactly. In classical planning, actions are basically instantaneous.
They take 0 seconds.
Right. The action eat lunch is just considered a state change. You literally just flip from a state of hungry to a state of not hungry.
Right.
It doesn't matter computationally if lunch takes 10 minutes or if it takes 10 hours.
Which is perfectly fine if you were solving, say, a sliding tile puzzle on a computer screen. But when you step into the real world,
Duration is everything. Real life demands to know, how long does step A actually take? And do we actually have the staff available to start step B while step A is still happening?
it's basically the difference between planning a menu for a dinner party and actually cooking the meal.
That's a great way to put it.
Because the menu just says, serve the roast. But reality says the roast takes 4 hours, the oven has been acting up, and I only own one roasting pan anyway.
Precisely. And this harsh reality brings us to the discipline of scheduling.
Okay.
Now, the source material highlights a really pragmatic strategy used in AI to deal with this, called the plan first, schedule later approach.
Plan first, schedule later. That honestly sounds exactly like my personal approach to long weekends.
Is that right?
Yeah, I make a list of 10 incredible things I want to do, and then Sunday night rolls around and I realize I've maybe done one of them.
Well, in the context of AI, it's actually a highly rigorous mathematical choice to manage complexity. It's not just procrastination.
Oh, good to know. So how does it actually work under the hood?
Think about the math involved here. If you try to solve for what actions to take and exactly what minute of the day to take them simultaneously,
It gets complicated.
the number of variables just explodes. It becomes computationally intractable very, very quickly. So to survive, the AI splits the problem in half.
Divide and conquer.
Yes, phase one is the plan. The AI completely ignores time for a moment and just figures out the core logic.
Okay, so it just figures out the steps.
Right. It says, okay, to build this car, we need to attach the engine, then we need to attach the wheels, and then we need to inspect it. It creates a solid logical chain of events.
So we have the basic recipe.
Exactly. Then it hands that recipe over to a separate function called the scheduler.
And what does the scheduler do?
The scheduler's only job is to apply the temporal information. It takes those constraints and makes sure the recipe actually fits the real-world deadlines and the resource limits of the factory.
So you don't even look at the clock until you actually know what it is you're supposed to be doing.
In this specific approach, yes, it greatly simplifies the problem space.
Let's ground this. Let's dive into a really specific example from the source material. They talk about being in a factory setting, a job shop.
Right, the classic job shop scheduling problem. This is a very famous benchmark in computer science.
Set the scene for us.
Imagine we are running a small assembly line, and we are building two cars, car A and car B.
Simple enough, 2 cars.
For each car, we have a specific set of jobs that absolutely must happen. Let's keep it simple. Add engine, add wheels, inspect.
Engine, wheels, look at it. Got it.
But here is where the constraints come rolling in. First, you have ordering constraints. This is basically just logical physics.
Right.
You obviously can't inspect the car before you actually build it. You can't put the hubcaps on before the wheels are attached.
That makes intuitive sense.
But then you add resource constraints.
Yeah.
And this is where the math gets incredibly tricky.
How so?
The text distinguishes between two very different types of resources you have to manage: consumable and reusable.
Consumable resources. That sounds like, what, snacks for the break room? Fuel?
In a factory setting, think of things like lug nuts, rivets, or glue. The source uses the example of having, say, 500 lug nuts sitting in a bin.
Okay, 500 lug nuts.
Putting the wheels on car A requires exactly 20 lug nuts. Once you do that job, those 20 nuts are gone forever. They're consumed. You cannot reuse them on car B.
Right, they're physically attached to car A now.
Exactly. So if your schedule ever causes you to run out of lug nuts, the entire plan halts. That is a consumable resource constraint. The AI scheduler has to actively track the inventory level at every single point along the timeline.
That sounds stressful. And what about reusable resources?
These are things like the engine hoist, the robotic welding arm, or the human inspectors themselves.
So things that don't get used up and disappear.
Right, they don't vanish. If you assign an inspector to a car, you occupy them for, say, 10 minutes. They are essentially borrowed by that task.
But they come back.
They do. But, and this is the crucial constraint, they are completely unavailable for anyone else during those 10 minutes. They have a maximum capacity of 1.
I can see how this feels like it could get complicated really fast. If I have an order for 10 cars and I only have one inspector on the floor, that poor inspector is a massive bottleneck.
A huge bottleneck. And this brings up a genuinely fascinating trick the AI uses to handle this kind of complexity without crashing. It's called aggregation.
Aggregation. What does that actually mean in this context?
Okay, imagine you're the factory manager. You have 2 inspectors working today, Alice and Bob.
Alice and Bob, the classics.
In a naive planning setup, you might try to plan specifically for Alice to walk over and check car 1 and for Bob to walk over and check car 2. You treat them as distinct individuals.
Right. I'm juggling their specific names and locations.
But computationally, that is wildly expensive. Because now the AI has to track two entirely distinct variables. Where is Alice right now? Where is Bob right now?
And what if I switch them around?
Exactly. If Bob does car 1 and Alice does car 2, is that considered a brand new plan? The system has to evaluate that.
I see. It just exponentially multiplies the options it has to calculate.
It does. So aggregation says, stop tracking Alice and Bob as individuals. Instead, just track a variable called inspectors and give it a value of 2. Treat them as a single pool of identical resources.
So the AI literally does not care who does the job, just that a body is there to do it.
Exactly. It groups indistinguishable resources together to drastically reduce the mathematical complexity.
That's wild.
The source material makes a really great point here to illustrate why this matters so much.
Let's hear it.
If you have 10 separate jobs and you have 10 individual inspectors and you try to assign specific names to specific jobs, the AI has to check all the possible permutations to find the best schedule.
Which is what, 10 factorial?
Yes, 10 factorial, which is over 3.6 million different combinations, over 3.6 million schedules just to assign 10 people to 10 jobs.
That is absurd.
But if you use aggregation, if you just tell the system, I need one inspector for this job and I have a pool of 10 available, the complexity drops to almost 0.
Because it's just checking a total.
All right, it just checks one simple math equation. Is the number of inspectors currently available greater than or equal to 1? If yes, proceed.
That is a staggering shortcut. It's kind of like highly efficient dehumanization.
Well, in a way, sure. It's treating humans as pure variables, which, for a mathematical algorithm, is absolute perfection. It turns a combinatorics nightmare into a very simple arithmetic check.
Okay, so we have our consumable resources, we have our reusable jobs, we've efficiently aggregated our inspectors into a faceless pool.
Yes.
How do we actually figure out how long the whole manufacturing process is going to take?
We use a tool that pretty much every project manager in the corporate world knows, even if they don't know the underlying math. It's called the critical path method, or CPM.
Critical path. It always sounds so dramatic.
It really is the heartbeat of any schedule. So picture a graph in your head. Bubbles connected by arrows. Each bubble represents a task.
Okay, I'm picturing a flow chart.
And the arrows point from one task to the next, showing the mandatory sequence. Now, some paths winding through this graph are very short. Maybe the sequence for putting on the decorative decals only takes 5 minutes total.
Right.
But some paths are very long. The sequence for dropping the engine into the chassis and wiring it up might take 4 solid hours.
Makes sense.
The critical path is defined as the single path through that entire graph that has the longest total duration.
Okay, but why is it called critical?
Because it completely dictates your finish line. You absolutely cannot finish the project until the longest continuous sequence of necessary tasks is complete.
So the longest chain rules the whole factory.
Exactly. If you have one sequence of events that takes 20 minutes and another parallel sequence that takes 4 hours, the whole project takes 4 hours, period.
So if I spend a ton of money to speed up that 20-minute decal task, it doesn't actually help me.
It does not help your final delivery time at all. You'll just have a guy standing around for 3 hours and 40 minutes waiting for the engine team to finish.
So this implies that if I want to get the car out the door faster, I should completely ignore the decals and focus every ounce of my energy on the engine installation.
Exactly. That is the core management insight of CPM. Resources should always be poured directly into the critical path.
Right.
Conversely, if you delay any action on the critical path, if that engine installation slips by even 1 single minute, the entire project is now 1 minute late.
That's a lot of pressure for the engine team.
It is. But for the decal team, the ones not on the critical path, they have what scheduler algorithms call slack.
Slack. I really like the sound of that.
Slack is the window of time that you can delay a task without hurting the final overall deadline.
So it's breathing room.
Basically, if the engine takes 4 hours and decals only take 5 minutes, the decal team has 3 hours and 55 minutes of slack.
They could take a nap.
They could go to lunch, take a nap, whatever. As long as they get those decals slapped on before the engine team finishes their 4-hour job, the car rolls off the line at the exact same time.
Note to self, always try to get assigned to the non-critical path.
We all do. But here is where it gets genuinely interesting and, frankly, really hard for the AI.
Okay, lay it on me.
Finding that critical path is basically simple addition if you only look at time.
Right, just add up the minutes.
But when you introduce resource constraints, when two different paths suddenly need the same engine hoist at the exact same time, the math problem becomes what computer scientists call NP-hard.
NP hard. We hear this term thrown around a lot in tech spaces. Break that down for someone who doesn't have a computer science degree.
In plain English, it essentially means intractably difficult.
Intractable.
It means there is no known shortcut, no clever trick to find the absolute mathematically perfect optimal solution. As the problem gets even slightly bigger, the time it takes a computer to solve it grows exponentially. It just explodes.
Can you give us a sense of scale on that? How hard is it really?
There's a very famous historical anecdote mentioned right in the source text. Back in 1963, a challenge problem was proposed in the operations research community.
Okay, 1963.
It was a standard job shop problem. It involved exactly 10 machines and 10 jobs.
That honestly seems tiny. 10 machines and 10 jobs. I feel like I could have figured that out on a diner napkin.
You would really think so.
Yeah.
But because of the overlapping resource conflicts, Job 3 needs machine A, but machine A is currently busy with Job 7, which is waiting on machine C, it creates a massive interlocking puzzle.
Right.
That little 10 by 10 problem went completely unsolved for 23 years.
Well, wait, 23 years?
23 years. It wasn't until 1986 that computers and search algorithms finally got sophisticated enough to mathematically prove the truly optimal schedule for just those 10 machines.
That is just wild to me. So if we couldn't even solve a tiny 10-machine puzzle without decades of academic work, how on earth does a massive operation like an Amazon warehouse run? They obviously can't wait 23 years to schedule my package delivery.
Right. The answer is they don't look for the perfect solution anymore. They use heuristics.
Heuristics, basically rules of thumb.
Yeah. Exactly. Smart shortcuts. The one specifically mentioned in the text for this kind of scheduling is called the minimum slack algorithm.
How does minimum slack work?
It's a very practical strategy for the AI. It basically says, look at all the jobs you could legally do right this second.
Okay.
Which one of them has the least amount of slack? Which one is dangerously close to becoming critical and delaying everything?
So just do the most urgent thing first.
Exactly. Schedule the critical stuff immediately. If a task has 0 slack, do it right now. If another task has 4 hours of slack, just push it to the back of the line and worry about it later.
It's basically the emergency room triage method of factory planning.
It is exactly triage.
Yeah.
It doesn't guarantee a mathematically flawless, perfect schedule. Maybe you finish your project 2 minutes later than the theoretical optimum.
You finish it.
Right. It runs fast on a computer, and it prevents catastrophic delays.
Okay, so that's scheduling. We are juggling time, we're counting lug nuts, and we're triaging tasks.
Yeah.
But let's zoom out for a second. You mentioned earlier in the show that a human life involves billions of discrete movements.
Billions and billions.
If my brain had to schedule every single muscle twitch using this minimum slack algorithm, I'm pretty sure I would literally never get out of bed in the morning.
And you wouldn't. This is known as the problem of scale. And it brings us right into segment 2, the hierarchy of action.
The source material actually had some genuinely terrifying math on this scale problem.
It really did. It estimates that a standard human life contains roughly 10 to the 13th primitive muscle actions.
10 trillion twitches.
10 trillion. And even just planning a simple 2-week vacation to Hawaii involves about 10 to the 10th actions.
10 billion actions just to go sit on a beach.
Think about what it takes just to pack your suitcase. Pack bag isn't one action.
Right.
It's extend arm, grasp the sock, contract bicep, rotate wrist, release the sock.
And then you have to repeat that for the other sock.
Exactly. And then the shirts. And then maneuvering the zipper.
If an AI actually tried to plan a vacation by listing out every single muscle twitch in a massive linear sequence,
The standard search algorithm would just crash immediately. The search space, which is the total number of possibilities it has to look through to find a path, is vastly deeper than the universe is old. You simply cannot plan at that granular level.
so obviously we don't think like that. I am definitely not thinking about my biceps when I throw a shirt in a bag.
No, you aren't. Because you think in hierarchies, and this is the AI solution as well. Hierarchical task networks, or HTNs.
HTNs.
We group billions of tiny little movements into what we call high-level actions, or HLAs.
Give me a concrete example of an HLA.
Go to San Francisco Airport. That is one single action in your mind.
Right, go to the airport, done, checkbox.
But to the AI planner, that one HLA can be what we call refined. It breaks down into smaller chunks.
Okay.
Go to Airport refines into, say, Drive to parking, park the car, take the shuttle to the terminal.
And then I assume drive to parking breaks down even further.
Exactly. It's fully recursive.
Yeah.
Drive becomes start the car, back out of the driveway, navigate the roads. Navigate becomes turn the steering wheel, press the gas pedal.
It's literally like Russian nesting dolls, but made of actions.
It is exactly like that.
Uh-huh.
And this, by the way, is how all large human organizations work too.
What do you mean?
The CEO stands up and says, increase sales. That's a massive HLA.
Right.
The vice president takes that and refines it to launch a new marketing campaign. The department manager refines that to design a new web ad. And the poor intern refines that down to click the mouse on Photoshop.
So the CEO never actually needs to know about the intern's mouse click.
Precisely. And in artificial intelligence, this architecture allows us to plan at a very high level without getting completely lost in the weeds right away. We can map out the entire Hawaii vacation using maybe 50 high-level actions instead of calculating 10 billion muscle twitches.
That sounds perfect. But knowing this topic, there is a catch. There's always a catch.
There is a significant catch, and it revolves around what researchers call the holy grail of planning, angelic semantics.
I really love this term, angelic semantics. It sounds so, I don't know, benevolent.
It's a beautiful concept, honestly, but it was invented to solve a very nasty logical problem.
Which is?
The problem is this. How do you actually know that a high-level plan is going to work if you don't check all the underlying details first?
Explain that a bit more.
Okay, suppose your top-level plan is go to the airport. You confidently put that block into your schedule.
Right.
But go to the airport has multiple possible implementations underneath it. You can refine it into drive your own car, or you can refine it into take a taxi.
Sure.
But driving requires that you own a working car. Taking a taxi requires that you have cash in your wallet.
Okay, I see where this is going.
If you blindly commit to the abstract plan of go to the airport, are you absolutely sure you can actually pull it off? What if your car battery is dead and your wallet is empty?
Then the whole high-level plan completely fails.
Exactly. And if you didn't check those specific details first, your high-level plan was basically garbage from the start.
But on the flip side.
Right. On the flip side, if you force the AI to check every single tiny detail of the taxi ride and the car engine before it even decides to go to Hawaii, you completely lose the entire computational benefit of the hierarchy. You're right back to micromanaging 10 billion steps.
So how on earth do we balance this? This must be where the angels come in.
Yes. The text introduces us a fascinating dichotomy. Angelic nondeterminism versus demonic nondeterminism.
Okay, I have to know. Who is the demon in this scenario?
The demon represents an adversary. It's worst-case thinking. If we say go to the airport and we assume a demon gets to choose how we get there, the demon is always going to pick the broken car. The demon actively tries to make our plan fail.
But in reality, we are the ones choosing how we get there.
Right. We are the agents acting in the world. We get to choose the method. So it's angelic. The angel is basically the agent's own ability to pick the specific path that actually works out of all the options.
So how does the AI actually turn that philosophy into a planning algorithm?
It calculates what are called reachable sets.
Reachable sets.
Imagine the AI looking at the high-level plan, go to the airport. It calculates two distinct things. First, the optimistic reachable set.
Optimistic. That sounds like calculating the best case scenario.
It is exactly that. It asks, is there absolutely any possible way this action leads to my goal? If everything goes perfectly right, if I successfully drive, or if I successfully take a taxi.
And if the answer to that optimistic question is no,
if the optimistic set doesn't hit the goal, meaning, look, even if everything goes absolutely perfectly, you still can't make it to the airport in time, then the plan is fundamentally flawed.
so you should just drop it.
You drop it immediately. Don't waste a single millisecond planning the details of a taxi ride if even the perfect taxi ride gets you there too late.
That makes total sense. That saves so much time. We prune the bad ideas early.
Exactly. But if the optimistic set does look good, then we calculate the pessimistic reachable set.
And what does that ask?
It asks, are we absolutely guaranteed to reach the goal? Meaning, no matter which valid refinement we pick, car or taxi, do we succeed regardless of the choice?
Okay, let's walk through the scenarios then. Scenario A, optimistic set says no.
The plan is dead. Throw it out.
Scenario B, pessimistic set says yes.
The plan is rock solid. Commit to it right now. You do not need to plan the underlying details yet because you know for a mathematical fact that you can achieve it when the time comes.
This is great. We can confidently make a massive plan without sweating the small stuff because we have a mathematical guarantee.
But then there is scenario C.
Always a scenario C.
The optimistic set says, yes, we might make it, but the pessimistic set says, no, it's not guaranteed.
So we might make it, but we also might fail depending on the details.
In that specific case, you must refine. You have to force the AI to dig exactly one level deeper into the hierarchy and check the next layer of details to be sure.
That actually makes perfect intuitive sense. It's exactly like my vacation planning. Yeah, I know that go to Hawaii is technically possible. That's optimistic. But I am definitely not checking the local bus schedule in Honolulu until I've actually booked the main flight.
Exactly.
I only refine the plan when I actually need to be sure the next step works.
Right. You don't plan the bus ride before you buy the plane ticket. That is angelic semantics in action. It mathematically allows the AI to completely ignore details until they actually matter for guaranteeing success.
So we have a rigorous schedule now, and we have a hierarchy so the computer doesn't melt down checking 10 billion details.
Right.
But both of those systems kind of assume we actually know what's going on in the world around us. What happens when the lights literally go out?
This takes us to segment 3, when the lights go out.
Hmm?
Or, as the source material more formally calls it, non-deterministic domains.
The text mentions that classical planning always assumes we have full visibility. We see everything on the board perfectly. But in the real world, things are, partially observable.
Partially observable, or in some cases, totally unobservable. The classic example given in the chapter is a robotic painting system.
Okay, let's set the scene for the listeners. We have a robot.
Yes.
It has 2 cans of paint sitting next to it. It has a chair and a table in front of it.
Right. And the goal programmed into it is very simple. Make the chair and the table the exact same color.
That sounds incredibly easy.
It would be, but here's the twist. The robot does not know what color the paint in the cans actually is.
Okay.
And it doesn't know what color the furniture currently is either.
Wait, so it's completely blind?
It might be physically blind, or maybe its camera sensor just broke. This scenario forces us into our first real-world strategy, sensorless planning, which is also aggressively called the coercion method.
Coercion. That sounds weirdly aggressive for a robot, like we are actively bullying the living room furniture.
It is a very brute force mathematical concept. The agent has no eyes, so it relies entirely on reasoning about what we call belief states.
Belief states.
Sets of possible worlds. It sits there and thinks, okay, the paint in can 1 could be red, or it could be blue. The chair could already be green, or it could be yellow.
So how on earth does it solve the problem if it literally can't see the colors?
It forces the physical world into a known state, regardless of what it started as.
How?
The AI solution is this. Open can 1. Paint the entire chair. Then paint the entire table with can 1.
Wait, it just paints them both blindly.
Yes.
But it still doesn't know what color the paint was.
It doesn't matter. The programmed goal was simply make them the same color.
Oh.
Right? If you paint the chair with can 1 and then you paint the table with can 1, logic absolutely dictates they are now the exact same color.
That is brilliant. So you don't actually need to know what the specific color is. You just coerce the physical world so that they match.
Exactly. You've coerced the environment into a successful state without ever sensing it. It's kind of like deciding to wash all your mismatched socks with heavy bleach.
Oh, I see.
You don't know which sock was red and which was blue beforehand, but you know for a fact they're all white now. You have systematically destroyed the uncertainty by just overwriting it.
That's remarkably clever, but also, frankly, a bit wasteful of paint.
It is.
What if the robot can actually see?
If it has sensors, then we graduate to strategy 2, contingent planning. This uses what the text calls percept schemas, meaning the robot can look and gather data.
So it doesn't just start spraying paint everywhere blindly.
No. The internal plan stops being a straight line and becomes a branching tree.
Okay.
It says, step 1, look at the objects. Branch A, if they're already the same color, stop right now, you're totally done.
Okay, that saves paint.
Exactly. Branch B, if they're different colors, look at the open paint can. Sub-branch 1, if the paint matches the chair, just paint the table.
It's very much if X happens, do Y.
Yes, the plan natively includes contingencies. It's vastly more efficient physically than painting everything, but the plan itself takes up much more computer memory because you have to store all those different branches and possibilities.
Now, there's a third way mentioned in the source, which honestly feels the most human to me. Online replanning.
Ah, yes, online replanning. This is the spot welding robot scenario.
Let's hear it.
Imagine a massive robotic arm in a car factory. Its only job is to weld a car door onto the frame.
Got it.
It is a very simple plan. Move the arm over, ignite the welder, weld the hinge.
Simple.
But then, real-world physics intervenes. The clamps slip, and the car door falls off the frame and clatters to the floor. Now, a dumb classical planner from textbook land might just move over and perfectly weld the empty air where the door used to be.
Because that was the script.
Right. It's blindly following the list.
Yeah.
Which is obviously not intelligent behavior.
No, that's a very stupid robot.
Exactly. But an online replanning agent actively monitors the world while it acts. It senses that the door is suddenly gone. It immediately pauses execution, and it triggers a replan.
It essentially thinks on its feet.
Yes. It calculates a new path. It puts down the welding torch. It picks up a gripper tool. It reaches down, grabs the door, lifts it back up, secures it, picks the welder back up, and resumes the original job.
It literally fixes its own mistake on the fly.
This is a huge leap. This makes the robot look purposive.
Purposive, meaning it has a purpose.
Right. It looks like it actually has intent. It's not just following a rigid script. It's actively chasing a final goal and adapting to get there.
The source talked a lot about execution monitoring here. I guess this is how the robot actually knows when it needs to freak out and replan.
Right. And there are different levels of monitoring.
Like what?
There's action monitoring, which is just checking immediate preconditions. Is the metal door actually physically there before I ignite my welding torch?
Makes sense.
Then there is plan monitoring, which is much broader. It's stepping back and asking, given that the door just fell off, will the rest of my entire 50-step plan still eventually work out?
And this capability leads to something I really loved in the text, serendipity.
Yes. Serendipity is such a great concept in AI.
It really is.
Serendipity is basically when the unpredictable real world actually helps you out by accident.
Give me an example.
Suppose the robot's final programmed goal is simply ensure the chair is red. It powers on, runs its plan monitoring, and its camera sees that someone else, maybe a human worker, has already painted the chair red while it was turned off.
It's a lazy robot's absolute dream.
Plan monitoring makes the system realize the goal state is already met, so it can just stop immediately. It doesn't blindly go over and paint the already red chair red again just because it was step one on its to-do list. It recognizes success and powers down.
But as with everything, there is a dark side to this replanning stuff, isn't there?
Dead ends. Dead ends are the major risk of constant replanning.
How does that happen?
The danger is that while you are adapting, you might accidentally act yourself into an inescapable corner.
Like what?
Imagine our painting robot again. It's online replanning, it's moving around, but it accidentally knocks the only can of red paint off the table.
Uh-oh.
The paint spills all over the floor and is completely ruined. The robot can trigger a replan all at once. It can run millions of calculations, but if there is physically no more red paint in the room, the goal is now mathematically impossible.
Right.
It has reached a dead-end state.
So you have to be really careful not to paint yourself into a corner. Literally.
Literally and metaphorically. Some actions in the physical world are simply irreversible. If you aggressively use up a consumable resource, no amount of clever algorithm replanning is going to magically bring it back.
Okay, so we've covered time and scheduling, we've covered the hierarchy of details, and we've navigated the fog of uncertainty.
We have.
But the final layer of complexity the text brings up is honestly the one that frustrates me the most in my own real life.
What's that?
Other people.
Oh, yes.
Segment 4. The social robot or multi-agent planning.
This is where the mathematical complexity just explodes off the chart.
Well, why is it so much harder? I mean, we just successfully handled broken factory doors and completely blind robots. Why is adding another person so difficult?
Because a broken car door doesn't have its own brain.
Fair point.
A door doesn't have its own secret agenda. When you introduce another agent, whether that's another AI robot or a human being, you are now dealing with a dynamic, highly unpredictable force that is also actively trying to change the environment.
Right.
And their internal plan might completely conflict with your internal plan.
The source text makes a distinction here between loosely coupled and tightly coupled interactions.
Right. Think of loosely coupled, like two people playing separate games of solitaire side by side on the same table.
Okay.
I'm playing my game, you're playing yours. We are physically in the same room, but my card moves don't really affect your card moves at all.
Yeah.
It's very easy for an AI to solve. I just run my plan, you run your plan.
And what about tightly coupled?
Tightly coupled is playing tennis doubles.
The tennis doubles example? I have lived this disaster many times.
This is the ultimate classic coordination problem in AI. You and I are partners on the court. The shared goal is to successfully return the ball over the net.
Okay, simple shared goal.
The ball is hit right down the center of the court. I rapidly formulate a plan in my head. I will run to the net to cover the short angle, and you will stay back and hit the ball.
That sounds like a really solid plan. I like that plan.
It is a good plan,
Yeah.
but you also have a brain. And your plan is, I will run to the net, and my partner will stay back and hit the ball.
Oh no. I see it happening.
If we both perfectly execute our own perfectly rational plans, we will sprint to the net, and the ball sails right past us to the baseline.
Or worse, we physically crash into each other trying to hit it.
Exactly. Even though we both share the exact same goal, win the point, and we are both acting completely rationally based on our own models, without active coordination, the entire system fails.
So how do we fix it? How do programmers teach these distinct AIs to actually play nice together?
The source lists three main mechanisms for coordination. First, conventions, which are basically social laws.
Like driving on the right side of the road?
Exactly like traffic rules. If we both pre-agree to the convention of driving on the right, we don't need to stop and mathematically negotiate with every single oncoming car we meet.
Right.
We don't need to rapidly replan every time we see headlights. We just blindly follow the convention.
So how does that apply to the tennis court?
The convention might be a rule like, the player with the forehand always takes the middle shots.
Right.
If we both internalize that convention, we instantly know who's supposed to hit the ball without even speaking.
That makes sense. What's the second way?
Direct communication. You literally shout, yours or mine.
Simple. Very effective.
It is, but computationally, it's quite costly.
Why?
It takes precious time to generate and process a message. In a split-second physical reaction, you might not have that time. And it requires open bandwidth. If there are 100 robots and everyone is shouting their plans constantly, nobody can process the noise.
Too much chatter.
Which leads us to the third and most advanced way,
Plan
plan recognition.
recognition.
This is the silent observational method. I actively watch your physical movements. If I see you suddenly take a fast step toward the net, my AI deduces your internal plan.
It reads your intent.
Exactly. It says, based on his trajectory, his plan is to rush the net. Therefore, I will silently update my own plan to stay back and cover the baseline.
It's essentially reading body language for robots.
Yes, it's inferring hidden intent from observable action. It's exactly what makes a really good human sports team feel telepathic. They aren't talking, they are just running constant, high-speed plan recognition algorithms on each other's movements.
Now, all of this tennis stuff assumes we're dealing with highly intelligent thinking agents.
Right?
But the source brings up something genuinely fascinating at the end of this chapter about ants, something called emergent behavior.
Yes, harvester ants are a brilliant example. They are a massive multi-agent system, millions of agents. But they absolutely do not have a 4-star general or a master queen bug barking specific orders and schedules at everyone.
So how do they actually get anything complex done?
They rely entirely on emergent behavior based on very local, simple interactions.
How does that work?
An individual ant decides what job to do today based solely on what it physically bumps into.
Really?
Yeah. If a forager ant is walking around and it constantly bumps into a lot of other successful foragers carrying bits of food, its simple internal rule says, hey, there's clearly a lot of food out here. I'll keep being a forager.
And what if it wanders around and bumps into nobody?
Its rule says, okay, I'm not seeing any successful foragers. There must be no food here. I will dynamically switch my role and become a patroller to check the perimeter instead.
So from the outside, the whole colony looks like this incredibly intelligent, centrally planned organism.
Right.
But the individual ant is basically just following a tiny, simple if-then rule.
Exactly. The intelligence isn't in the ant, it emerges from the system. And the exact same mathematical principle applies to flocks of birds.
Yeah.
The text mentions the classic Boids simulation,
Oh,
spelled B-O-I-D-S. It's a very famous computer graphics simulation created back in the 80s.
Okay.
The goal was to simulate a flock of birds on a screen that actually looks realistic. You know how they move like liquid swooshing through the sky?
right. That synchronized swooshing. It's beautiful.
Right. And the trick is, the programmer does not program the swoosh.
They don't.
No. You don't program a leader bird, and you don't program flight paths. You literally just give every single individual bird 3 incredibly simple geometric rules.
What are the rules?
Rule 1 is separation. Don't physically crash into your immediate neighbor.
Okay, good rule.
Rule 2 is alignment. Try to fly in roughly the same compass direction as your immediate neighbor.
Makes sense.
And rule 3 is cohesion. Try to stay relatively close to the physical center of the birds you can see around you.
And that's it, just those three things.
That is literally it. If every single digital bird independently follows just those three tiny local rules, the massive complex flocking behavior just organically emerges on the screen.
Wow.
It looks exactly like a giant, highly intelligent, coordinated organism, but it's really just thousands of independent agents following simple laws.
It really is beautiful. And I guess it shows that you don't always need a massive top-down master schedule to actually have a functional plan.
Precisely. Sometimes planning is just about setting up the right local reactions and letting the system run.
Well, we have covered a massive amount of ground today.
We really have.
We've gone from the ticking clock and the consumable lug nuts of the job shop to the nested hierarchies of our Hawaii vacation, through the blind fog of sensorless uncertainty, and finally onto the tennis court with our chaotic robot partners.
We've effectively watched AI move from the pure, isolated mind of the classical planner into a physical body acting in the real world.
Right.
We gave it a clock, we gave it resource management skills, we gave it eyes to check its work, and we gave it the rules to handle neighbors.
And the really big takeaway for me connecting all these dots is this concept of uncertainty management.
Yes.
The fundamental difference between a basic desktop calculator and an autonomous robot is that the calculator safely assumes the numbers are never going to change while it's busy adding them up. But the robot operates knowing full well that the numbers might literally run away while it's looking the other way.
Or the numbers might get painted the wrong color entirely.
Yes.
Yes. The true mark of intelligence in the real world isn't just the raw ability to solve a puzzle.
What is it then?
It's the ability to notice that the puzzle pieces themselves are physically changing shape while you are holding them, and adapting to that without freezing.
I love that. Now, I want to end today on the final, really provocative thought from the very end of the source material.
This is a good one.
The story of the Sphex wasp.
Ah, yes.
Mm-hmm.
The Sphex wasp. This is such a haunting little biological story about the true nature of intelligence.
Tell the listeners what this bug actually does.
So the Sphex wasp has a very specific reproductive routine. It goes out and catches a cricket to feed its larvae.
Okay.
It physically drags this paralyzed cricket all the way back to the edge of its underground burrow. It drops the cricket exactly at the threshold.
Mm-hmm.
Then it leaves the cricket, goes deep inside the burrow to inspect it, basically to make sure there are no predators inside, and then it comes back out to finally drag the cricket inside.
That honestly sounds like a highly prudent, intelligent plan. You know, inspect the house before entry.
It really looks very intelligent. It looks highly rational, but behavioral scientists did a really cruel little experiment.
What did they do?
While the wasp was deep inside inspecting the empty burrow, the scientists reached down and moved the paralyzed cricket just a few inches away from the door.
Just a little prank.
Right. So the wasp comes back out. It clearly sees that the cricket has been moved. It dutifully walks over, grabs the cricket, and drags it right back to the threshold of the door.
Okay, adapting to the environment. And then does it drag it inside?
No. It completely drops the cricket at the threshold again.
Yeah.
And it turns around and goes all the way back inside to inspect the burrow again.
Wait, even though it literally just inspected it 10 seconds ago?
Even though it just inspected it. It is entirely hardwired. And the crazy part is, if you wait for it to go inside and you move the cricket a few inches away again, the wasp will come out, drag it back, drop it, and go inspect again.
You're kidding.
It will do this 40 separate times in a row. It will literally do it until it dies of physical exhaustion.
That is insane.
It absolutely cannot skip the inspect burrow step in its internal programming. It fundamentally cannot reason, oh, I just looked in there, nothing has changed, it's fine to skip to the end.
It's just totally stuck in an infinite loop.
Exactly. It creates the incredibly convincing illusion of thoughtful, hierarchical planning.
Yeah.
But underneath, it is actually just a completely rigid, inflexible set of reflexes.
Wow.
A specific physical trigger strictly leads to a specific physical action. If the trigger state accidentally resets, the entire action sequence resets with it.
That is deeply, deeply creepy to think about.
It is creepy.
Yeah.
And for researchers, it forces us to ask a very uncomfortable philosophical question. We spent this whole hour talking about online replanning today. The advanced ability to actively adapt to new realities.
Right.
But how much of our own daily human behavior is actually true, conscious, intelligent replanning? And how much of what we do is just a really complex biological set of Sphex-like reflexes.
Wow. Are we actually truly planning our daily lives, or are we literally just dragging the cricket back to the doorstep over and over and over again, simply because that's what our internal biological loop tells us to do?
That is exactly the question. When you hit a sudden snag in your own real world, do you actually thoughtfully replan? Or do you just mindlessly repeat the exact same broken subroutine and hope for a different result?
Well, that is definitely something for you to think about the next time you lose your keys and check the exact same pocket 4 times in a row. Thank you so much for joining us today to unpack all of this.
It was an absolute pleasure.
We will see you all in the next deep dive, and until then, hopefully we won't get stuck in a loop.